Okay, today we're going to talk about the p-test, which is a shortcut to some common improper integrals that we see, so we don't always have to directly evaluate them. So let's zoom in here. All right, so the two common ones are the integral from 1 to infinity of 1 over x to the p, and the integral from 0 to 1 of 1 over x to the p dx, where p is some positive value. So we're going to look at three cases. The first one is if p is 1. So if p is 1, you just have 1 over integral from 1 to infinity of 1 over x, which we learned in the last video. We should start by rewriting. Limit as b heads to infinity, integral from 1 to b of 1 over x dx. And that equals limit as b heads to infinity. Antiderivative is natural log of x, and we're evaluating it from 1 to b, so we'd have natural log of b minus natural log of 1, which is 0. So I'm going to be lazy and not write it. And natural log of b goes to infinity as b goes to infinity. So this one diverges. Okay. Similarly, the integral from 0 to 1 is also improper. That one less obviously slow, but there's a discontinuity when x is 0. We would have an asymptote. So this would be equals limit as b heads to 0 from the other way, of integral, here, I didn't mean to use a b. I like to use an a for that lower bound. A heads to 0, a to 1 of 1 over x dx. And that's limit a heads to 0 on the right of natural log x from a to 1, which is natural log of 1, 0, minus natural log of a. Okay? So as a heads to 0 on the right, natural log of a is going to go to negative infinity. So negative infinity, this is going to go to infinity. So this also diverges. So now that we've essentially proven this case, anytime you encounter an integral of 1 over x dx, where either the upper bound is infinity or the lower bound is 0, you can say that the integral diverges by the p-test, and you don't have to do all these in-between steps every time. This thing comes up so often that this is a nice little shortcut. Let's also think about this graphically. If we look at the graph of y equals 1 over x, this is saying, let's grab some highlighter colors, that this yellow area here is infinite. So it's getting wider, as we're going to infinity, essentially faster than it's getting shorter. So in the race between getting shorter and getting wider, the wider wins, and so this area is going to go to infinity. Similarly, from 0 to 1, this area is getting taller as we approach 0, right? And the race between getting taller and getting narrower, the getting taller is winning. So this area is also going to infinity. So both of those sides are infinite. So I like that as a nice visual of thinking about the situation. All right, so now we're going to look at the next case. We looked at p equals 1. How about if p is more than 1? Well, let's look at this case down here. So if p is more than 1, all right, so this we're going to rewrite with a limit as x approaches b. That's silliness. That's not what I meant. As p approaches infinity, try that again, of the integral from 1 to b of 1 over x to the p dx. Now, this algebra is sometimes a little tricky for people. So we're saying we have 1 over x to the p where p is more than 1. So let's do this. Let's rewrite it as x to the negative p. That might be easier to undo the power rule for. So if we undo the power rule, limit as b heads to infinity. When we undo the power rule, the power gets bigger. So we'd have x to the negative p plus 1 over negative p plus 1 from 1 to b. So remember, p is more than 1. So this power x to the negative p plus 1 is still going to be a negative power because negative something more than 1 plus 1. So this is going to equal let's see how we're going to do this. Limit b heads to infinity of, well, it's going to be tight to squeeze in here. Never mind, we're going to go to the next line. Okay, down here. Limit b heads to infinity of 1 over negative p plus 1 x to the p minus 1. So I just rewrote it so that the x is in the denominator to help us think about this, and this is from 1 to b. So I just took the opposite of negative p plus 1 to put it in the bottom, which is p minus 1. b heads to infinity, 1 over negative p plus 1, x to the b minus 1, minus 1 over negative p plus 1. So I evaluated it at b minus the whole thing evaluated at 1. And remember, keep in mind what's going to infinity. B is going to infinity, right? Oh my God, what did I do? Silliness, hang on. Back it up, put the b in the wrong spot. B to the p minus 1. Okay, there we go. So b is going to infinity, so this first part here is going to go to 1 over something very, very large, right, which is going to be very, very small. So that's going to go, the first fraction is going to go to 0, and so we'll just be left with that second one, which is minus, so let's see, probably the easiest way to write that is 1 over p minus 1. So I'm just rewriting this. There. Okay, so this goes to a value. And depending on p, that'll be a different value, but what we've just found is that this converges. Okay, cool. So the last one, they both diverged. This next one, at least the first case, it converges. So now that we've done that, we can do a similar thing with 0 to 1. And so we've got limit as a heads to 0 on the right. Now I've already done the antiderivative, so let's sort of jump ahead. 1 over negative p plus 1, x to the p minus 1, from a to 1. So I shortcutted it because it's the same integral except for the bound, so I just copied that down there. So that equals, limit is a heads to 0 on the right, 1 over negative p plus 1, a to the p minus 1. Oops. Put that in the wrong order. We'll get there. So 1 over negative p plus 1 is the top bound, minus 1 over negative p plus 1, a to the p minus 1. Okay. So now as a goes to 0, we've got this first part, which is a constant, and then the second part, the denominator is going to get very, very small, right? Because a is going to 0. So 1 over a very, very small thing is very, very big. So we'd have 1 over negative p plus 1 times, and then times infinity. So this is going to go to positive infinity, because negative p plus 1 is actually a negative value. So it would be negative something, minus negative is plus. All right, so let's add some stuff to the graph. So notice both of these have a cool thing, which is all 1 over x to the p graphs go through the point 1, 1. It was kind of just neat to know. So the first one we did was this. So when it's something like 1 over x squared or 1 over x to the 5th, when p is more than 1, this area is actually finite. It converges. Meaning 1 over x squared, 1 over x to the 5th decreases faster than it gets wide. Okay, whereas 1 over x didn't. So as soon as we have a higher power of x in the denominator, this yellow area then converges as we go to infinity. And then let's look at this other area, the green area. I just realized I didn't write something. Since this equals infinity, this integral diverges. So from 0 to 1, this integral is infinite, it diverges. So 1 over x squared, 1 over x to the fifth, 1 over x to any power more than 1, it's increasing faster than it's getting narrow. So this area is infinite. So infinity, infinity for 1 over x, infinity converges for 1 over x to a power more than 1. All right, so one last case to look at, and then we can kind of summarize and show you how to use it. So there's the whole page. If you wanted to see that, go ahead and pause. All right, last case. What if x is less than 1? All right, so two cases to look at. If x is less than 1, we're going to, again, rewrite with the limit, because we do that anytime we're evaluating an improper integral. And let's see, I'm going to write this like this. X to the negative p dx from 1 to b equals, limit b heads to infinity. So x to the negative p, remember we're undoing the power rule. So we have x to the negative p plus 1 over negative p plus 1. So this looks exactly like what we had on the last page, right, with the last case. Except if p is less than 1, negative p plus 1 is now a positive value. So I am not going to put that x in the denominator, because x to the negative p plus 1 is x to a positive power. All right, so let's try doing this one. Limit b heads to infinity of b to the negative p plus 1 over negative p plus 1 minus, and when x is 1, it's just going to be 1 over negative p plus 1. Okay? So as b goes to infinity, since this is infinity to a positive power, that's going to go to infinity. So it diverges. All right, let's look at the opposite case. We can save ourselves a couple steps because we already evaluated this integral. I'll write it as limit as a heads to 0 on the right. And I'll jump ahead to the antiderivative. X to negative p plus 1 over negative p plus 1 from a to 1 equals limit 0, right, a to the negative p plus 1 over negative p plus 1 minus 1 over negative p plus 1. Okay, so now a is going to 0, which means this first fraction is going to go to 0, because 0 to a power, a positive power, is going to be approaching 0. So this is going to actually come out to just the second part. And now we have minus a negative, so let's rewrite that as taking the opposite of the denominator, 1 minus p. So that converges to some positive value since p is less than 1. All right, again, let's think about it graphically, because I'm a big believer in the graphically way to kind of visualize it. Let's grab yellow here, and green here. Okay, so in this case, the integral on the right diverges. It's going to go to infinity, okay? So this is any time where you have 1 over x to a power where the power is less than 1. So 1 over square root of x, 1 over x to 2/3, any kind of power less than 1, like often a fraction. So on the right, 1 over square root of x, 1 over x to the 2/3, etc., decrease too slowly. So in a race between getting wider and getting shorter, it's getting wider faster than it's getting shorter. So this yellow area is infinite in this situation. And then we saw from 0 to 1, this area actually, the green area actually converges. Okay? So 1 over square root of x, 1 over x to the 2/3, all of those are going to approach the vertical asymptote quickly enough so that they're going to get narrower faster than that area gets taller. And so that's why that area converges, okay? So again, just to sort of compare, picture this, and then picture this. So infinity, infinity, infinity converges, and then the reverse converges infinity. So this is to help you kind of remember the three cases of the p-test, okay? Now I want to show you a couple examples of using the p-test. So here's two problems. So could we do these problems by actually evaluating? Yes, we could, but no thank you. We're going to do a shortcut. So first thing we're going to do is rewrite this. 2 to infinity. We have cube root of x over x, which is the same as 1 over x to the 2/3 dx. So p here is 2/3, which is the less than 1 case. And so we look at this and we say this is from 2 to infinity, so it's like this here, right? And that diverges. So you would say this diverges by p-test, and then specify p equals 2/3, which is less than 1. Okay? That's all you have to do now, if you can get it in this form. Now notice that number isn't a 1, right? So it doesn't actually matter in this picture we have up here whether I break it at 1 or I break it at 2 or somewhere else. The convergence or divergence is, you know, way off on the right or way over on the left. So this lower bound not being a 1 is okay. As long as it's on the right side of the asymptote, so it's some positive value, it doesn't actually matter what that 2 is. The convergence or divergence happens way out here at the end and not, you know, close to the 1. So it doesn't matter if we started at 2 or 3 or 5 billion instead. Okay, so that's a big time saver, isn't it? Here's another one. Now this one is kind of weird because there's no infinity in the upper bound and there's no 0 in the lower bound. And you're like, oh, bummer, can't do the p-test, but you can. So all you have to do is say, let's make u equal x minus 3. Well then, du is dx, so this is going to be a great u sub. So it's going to be 1 over u to the 3rd, du. And then all I have to do is update my bounds. So if x is 3, u is 0. And if x is 6, u is 3. Now does that look like the p-test? Yes, it does. We have 1 over u to the 3 from 0 to 3. So again, let's go remember the situation. So p is more than 1, so it's this situation. And so it's this area here, and that area diverges, okay? So what we can do by doing just a little u sub is saying now this diverges by p-test with p equaling 3, which is more than 1, okay? Now, I notice I just accidentally chose 2 examples where it diverges. You can also use the p-test to show that something converges. That's completely legit. So what we're learning here is if you can just do a little algebra or a little u sub to get it into the form 1 over x or whatever variable to the p, you can quote the p-test and save yourself some steps with limits. Okay? So that, here I'll do a zoom out so you can see the whole thing in case you needed notes. That is the p-test, ladies and gentlemen.